Hello? Hello?
All right.
Hello? Oh, you're all still here. This is unbelievable. You're all still. Can you hear me? Or see?
Yeah.
Hold on, hold on. I cannot hear you. Can you hear me? Yes, you can. Okay, thank you. I can someone say something so I can see if I can hear you?
Hi.
Hi. Okay, thank you. All right. This is crazy town. All right, thank you. I can't believe you're still hanging in, all of you. Like seriously, again, if grades are based on anything like what they should be, any one of you who's sitting here right now should only feel increasingly confident about their grade, not because, but because this is crazy. Okay, thank you. I seem to be, I'm outside now in a different building. Hopefully this will work. Again, I'm even more embarrassed than I was before. What I was trying to ask you guys was to basically look for questions about the material. Like uh, yeah, I mean, I think it would be very difficult to learn so far. But there is material to be learned and there is material that's been presented. So what I'm trying to say is if anybody can give me a concrete question, like, can you explain omega or oh no, did I just lose you again? Wait, no, okay. If anybody has any question, like, or even like, I don't see what, how to do a cosine or something, I would be happy to answer. I mean, if not, I am just going to go on right now, obviously, but if nothing else, please, like, know that while I'm talking, while I'm doing stuff, especially when I'm actually here and less conflicted, if I'm doing some mathy thing for you all, if you can even have the presence of mind to recognize, oh, he just wrote down a line that I just totally don't get. Like, I just don't even know what he's talking about. If you could, like, it may be that you don't want to stop and say that to yourself because you, whoever, all of you are, it might be like you realize I've never really understood cosines. Therefore, I don't understand that statement. Like, that's a tough thing to say in a group, I know, but I kind of am here to say, like, if we want to learn whatever we can learn so that we can learn. So anybody who's willing to say what they do or don't get is just going to make the class better for anybody. So I'm gonna like I'm looking at the chat. I see a thing happening in the chat. Oh my God, something substantive in the chat. Oh wow. Wow. Okay, that is a so Robert's remark in the chat, very honest, very fair, very persuasive. I totally hear. I mean, wow, that's very helpful. Okay, okay. That okay. That is very helpful. It's so helpful that, of course, I want to admit, of course, a little bit of it is a little bit like hard to hear or something like, but not really. Like, I totally get it. Okay, and part of me wants to say, okay, from here on in, I will, well, I will try much more to give a context to all of this, to what we're doing now, and to what's about to happen. There's a little part of me that wants to say that sometimes that is deliberate, maybe good, maybe bad. Like, it is true that thing on the spring itself, very much, you're right. Thing on the spring absolutely does not start off by saying anything about harmonic oscillation. It doesn't. And we do at the end say, like, so what we've been trying to build up is this thing that we're now going to call harmonic oscillation. And I think that can make it very hard and mysterious. It is intentional that we do that. I do have reasons, but I'm not going to, like, and maybe later I'll try to explain them or whatever. But rather than trying to defend that, no, I'll try to give more context right now. And foregoing. The thing is, no, and that is very fair. I'll think about that more deeply, like when we're not all talking together. The real context of the whole class is that we are trying to study the motion of things that are not things, as abstract as that sounds. But that's like the larger context is ultimately we're trying to study the motion of waves and fields, which are not actually things. They're not matter. So where this is all going, the context of all this is, we're ultimately, in a day or two, in a week or two, we're really going to be directly, or if you're not already in the lab, we're going to be directly, explicitly studying waves, specifically sound waves. Let me start writing this down, in fact. Hold on. I think I can help with context here. I think that's a very fair thing to say. Hold on. Let me put it another way. It's 100% fair thing to say what Rob put in the chat, and a gutsy thing to say. It doesn't mean I can 100% like solve the problem of context right now, but it does mean I will have that very much in my mind as we go forward. And I will try right now to address context a bit before we do anything more. So yeah, so
For me, I think what would help a lot is if we had like something general that applies to the entire homework, because I know the homework has like different parts, but like for instance, the last time we had class and we worked on dx over dt is equal to negative k over n times t, something like that.
yeah,
I feel like that's very specific. And then in the homework, it kind of moves on to like other aspects of that same topic, but then we don't really get a chance to cover it in class. So I feel like what would help is if we had like a general guideline of how to answer specific problems like that. Because on an exam, it wouldn't be like just using that one thing that we learned in class and that's it. Like there would be a lot more questions. So what I'm trying to say is like that one thing that we learned in class doesn't really, it helps for that particular topic, but it doesn't really help me answer the rest of the questions. So I find myself not being able to use what we learned in class to complete the homework.
got it. All right, that's also fair too. Well, one thing I definitely think that I want to do then, one thing is I'm not going to assign any new homework because I do recognize that struggle. So it is absolutely true that I want to carefully finish going through the problems in the mathematical methods things before we go on. I'm going to write this context thing first and then do it. And I definitely, and yes, the big struggle, especially after other science classes our whole lives, it's true. We focus here. I tend to focus very hard on very specific examples. And then it can very much look like there's a million other examples or different problems like in a homework or an exam. And it can definitely feel for a while like there's no connection between the one like big example we do in class and the various others. So I want to work on that more too. You're right. And give you, and it will help if I go through those other examples like today and Tuesday and try to show you how they're related to that one. But there's bad news and good news about that also, because that's also super fair to say. The bad news is that in some ways that's always is the difficulty of physics. Like in a way that is what's hard about physics is that like we're trying to study a couple of key historical example problems and then learn from them how to tackle problems that we don't know how to tackle. Like that, the trickiness of all this is that actually secretly, I don't want anybody to learn. I mean, we all want them, but we don't really, in the long term, want to teach procedures for solving specific problems. We want to teach procedures for what to do when you don't have procedures. I mean, as weird as that sounds, but that does sound weird and that does sound not helpful and abstract. So here's the more concrete thing. The more concrete thing, because again, that's totally fair. And I really do appreciate like the clarity and the guts and the honesty and the correctness of what like at least two people have said so far. And there may be more in the chat, but like to be more concrete too, at all times, I know that a lot of this is confusing until it isn't. Like, and it certainly was for me, and I'm trying to make it less, but I know that this is confusing until it isn't. One thing is that I'm also intentionally delaying the issue of an exam because, I guess you know this from 203, but when we get to an exam, remember what's going to be on the exam is whatever's on the practice exam. Like it is true that this method of learning, what I'm doing, like if I spend 3 days on one big example and then through an exam with all these different things that you didn't even know to expect, that there'd be no hope for anybody. That would be outrageous. One thing I do want to say is the one example that we do over and over again actually is like, we actually don't want you to know as many things as in other classes you're used to knowing. Like there's a big fear that there's going to be a million of these things that you have to keep track of. Actually, I really only want us to really get a couple of major problems. And if we really know them inside out, other things that seem different will seem more similar. But that's what I think it sounds like I should really do is I just want to finish quickly writing down what the context is a little bit to answer Robert's thing. And then I want to actually go over those problems from the math methods like Rain is asking about, because I think that will help too. Also remember, everybody, please, I do get like doing the homework is really like every new physics problem to all of us, I mean, to me, to Walters, any new problem I get in physics ever, if I haven't seen it before, it always looks like something totally new. And the whole trick is to try to see how to model it after something I've done before. But I'm not saying we're there yet, but yeah, let me go over the other problems in math methods and try to show how they are kind of similar. But yeah, also don't, no matter what I say today, if it helps anybody in any way, even do one more problem, then just hand that in. Anything you get from this at any time, you just hand it in, like in the homework slot. It will be credit worthy, and I definitely don't expect people to get things until they do. But yeah, I also don't want to waste it. I think these are good, and keep these coming, these comments. But let me finish writing down what I was saying about context to Robert, and then we'll actually do some of these problems. The big context of this class is, so the big context of this class is waves, really, and then ultimately fields. Sorry. And the thing is, just to put it a little bit in perspective, not that it doesn't help you solve the problem yet, but just where this is going is we're trying to get ourselves to the motion of waves. First, for example, like water waves, but then more specifically like sound waves, and ultimately light waves. And waves are immaterial motions. What they consist of is lots and lots of little bits of material harmonically oscillating. Like we are now analyzing a harmonic oscillator. Like it may all feel like this harmonic oscillator is just one little example of a million things that we have to do, but no, it's actually like a third of the class is this harmonic oscillator business. We're studying the crap out of, or analyzing the crap out of a little vibrating system and getting really detailed with it, because the idea is once we really understand how vibration works, we're going to put in our minds and in reality a bunch of vibrating systems, like a bunch of oscillators next to each other, and they're all going to oscillate in succession, like in a rhythm, like one up, one down, then the next one up, down, then the next one up, down. And that's how we make waves. Like in reality, like that's how waves form, and that's how we understand them. And here's really the thing, just, so let me write this down. So waves consist of multiple harmonic oscillators. The wave equation that we're ultimately trying to build from all this and use, the wave equation is a second order differential equation built from the SHO equation, the simple harmonic oscillation equation. In other words, and this again, I know I probably sound defensive, and it sounds like anything I say in response to someone's question, like I'm sure it sounds like I'm arguing their question, and I really don't mean to be. I really think these questions are exactly what, or these comments were the kind of thing I'm looking for, which, doesn't mean that like, whatever, it's exactly what I'm looking for. So, but what I want to say here is, if it helps at all to know, all this analysis of harmonic oscillation and of that one equation that, like we did this dx dt thing equals blah, blah, t. Then we did this dx dt thing equals blah, blah, x. They look very, very specific, and they look like just specific cases of some larger understanding that you might feel that you don't have yet or something. But actually, they are the thing that we're looking at. We're looking at a specific kind of differential equation called, and it's the first one we've all ever seen, so that's why I'm like talking about it a lot. But we're looking at a differential equation, which is the one that describes harmonic oscillation. Why we care so much is once we get that equation, and I'm trying to get it piece by piece, but once we get that equation, then we build from it a slightly more complicated equation, which is also a second order differential equation. And that one governs waves. Like where the context of this is, we're trying to understand enough math of oscillation to understand the math of waves, so that ultimately we can understand fields and light. Like, but that's what. So every little math example we're doing is actually meant to try to get us practice with the pieces that we need for this math. I mean, and that's, so I should get to it, obviously. But I guess the flip side of what I'm saying is the reason we focus so much, it's really not like a math class where you have to learn a whole topic of math and we're going to ask you a bunch of million different exercises on the exam or the homework and you have to see the whole broad thing. No, we're trying to teach very specific math equations. So I'm unpacking them as much as I can to get them. But if you get the equations that we're actually doing here, they don't represent a larger whole, they are the whole. But all right, I'll show you what I mean. I'm going to turn right now. Again, I'm going to take those two comments even more seriously. Like I'm going to think more and try to say more about those two comments tomorrow or any other comments like that. I do appreciate the honesty. Right now, it sounds like the best thing I could do is start going over these examples from the math methods homework sheet. That's what I'm going to do right now for whatever 40 minutes we have. Stop me at any point. I'm just pulling it up. And again, this does not assume you can still do it. You could still start it. You could still finish it. I'm just going to start talking about it or continue talking about it. So we're talking about homework 3, the math message sheet. I'm just pulling it up. Okay. Okay. So I'm looking at it. I hope you all are looking at it. I'll try to do a screenshot of it in a second, but I'm talking about, it's actually homework 2, mathematical methods. And all right, I'm just going to go through it actually from the beginning, just straightforwardly, because hopefully that will. Are we still all here? Are we still here? Oh, but you're not seeing my board. Hold on. All right, I'm going to start talking about it while my board warms up. The first question on it is derivatives. Okay, given x equals a cosine omega t. Now, and then it asks you to find the first derivative and the second derivative. Now, that could be just an abstract math thing, like, and I'm going to treat it that way first. And when in doubt, if one doesn't understand the context, if one can just like take it step by step, that's the best thing. So even if I don't know why this is being asked, and there is a reason, but even if I don't know why this is being asked or what it has to do with physics, the answer to A sub 1, I'm just waiting for my board to get an internet connection, but the answer to A sub 1 is dx dt equals negative A omega times sine omega t. I'll say that one more time. I can't seem to write it down at the moment because I can't seem to get my board. But the answer to 1A1, to Roman numeral 1 derivatives, part A, the very first question on the math method sheet, it asks you for the first derivative. And the answer is dx dt equals negative A omega sine omega t. The reason that is the answer, I can't believe we don't differential. The reason that's the answer is the derivative of cosine is negative sine, but you also have to use chain rule because this is a function of a function. So it's actually a function of omega t. So the derivative of omega t is omega. So you have to multiply your whole answer by that. I cannot believe that I do not have internet. One second. So the first derivative is, and I'm going to just keep talking until I can get a board here, is dx dt equals negative A omega sine omega t. Then the next question is, what's the next derivative? Like, can you take the derivative of that? And you do the exact same procedure, only now the derivative of sine is cosine, and you don't play with the negative sign. Like the derivative of cosine is negative sine always, but the derivative of sine is just cosine always. So the answer to this next one is d2x dt2 equals negative A omega squared cosine omega t. That's an important answer. That's the answer to A1, 2. Now, again, I am just trying to, hold on a second. Can I just see, I know I didn't write that down, but I said it. Can anybody just show hands if you heard the answer, if it's clear what the answer is? Thank you. I totally appreciate that. Okay. Does anybody want to ask anything about that? Like,
I heard it, but can you repeat the last one more time?
absolutely, I'd be delighted. Yes, and I'm working on my board as I say it. But yes, the last answer, the second derivative is negative capital A omega squared times cosine of omega t. That's the answer to the second derivative. Okay, wait, I might have my board now. 1 second. Did that work?
Yeah.
Okay, cool. Thank you. And again, I'm gonna keep I want to keep coming back to what both like Robert and Rain said, because it really was valuable. And again, like, look, of course, any even constructive criticism is always like a little bit emotionally like tricky to hear. So I want to give it full weight. Like, I just want you guys to know that I'm going to have, even if I didn't answer what they said perfectly, it's in my mind now as we're talking. So like, as we're going through the sheet, and I think I do have a board again. Wait. As we're going through the sheet, like, well, let me just try. Those are the answers. But yes, if I'm a student just looking at this, this could look just like, here we go. Do you see my board now? Wait, can you see? Yeah, can you see the board now? I think. Okay. These look like just random. Oh, great. All right, thank you. They look like just random exercises in derivatives, but the truth, and they are exercises to make sure we understand how to take derivatives. But really, I'm intentionally asking about that function because that function turns out, that cosine function turns out to be what best describes an oscillator, a harmonic oscillator, a thing going back and forth. And it best describes it for the reason that we're trying to see here in the math. So now I'm just writing what I just said. Okay. So just by straight calculus, these are the answers to each. Doesn't mean, but that's the answer to each. But now why, like, who cares? To try to get it to context is this part B, where it now says, is x equals a cosine omega t a solution to blah, blah, blah. Now, this is a weird question. This is what we're here to study. It's a very real question. And you may notice, I do ask it like a million times in this sheet. So if you don't get it, when you don't get it the first time, it does look like a million different things that one doesn't get. But it's really one new thing. The thing here is we're used to, in math and physics, we're really used to people asking us questions and then we give an answer. And more specifically, you're kind of used to like in science, like, someone asks a question and in order to get the answer, what you need is an equation. But here, what we're really saying is at this level of math and physics, questions are answered by equations. What we look for in math and physics at this level is we're looking for functions. We're looking for the way to describe a mass on a spring. And what the physics told us, like what Hooke's law is a purely physical thing, right? That said this, so I'm backing up just, but since we also have Newton's law, I'm saying this fast because we've said this a million times, but since we had Hooke's law from physics and we have Newton's second law from physics, we put them together and we said, okay, that when a spring is operating on a mass, this is what's going on. When only a spring, a good, well-behaved spring, is pulling on a mass, what we have is negative kx equals ma. But since a is defined to be the second derivative of position with respect to time, like since there is that link to calculus in the concept of acceleration, what we found from physics was this last statement on the board. Divide both sides by k, and we have this. So physics, just our desire to just look at an oscillator physically, suddenly brought us to this equation here, outside the homework. I mean, from homework 1 is what homework 1 is trying to show. And this business in the parentheses happen to be physical parameters, things that describe physical materials in the world, the stiffness of a spring, the heaviness of a mass. But as far as math is concerned, everything in that parentheses is just some constant, some number that we don't know what it is or don't need to know, but we know it doesn't change. What this question now is asking in B, like B is, instead of saying, here's our question, what's the answer? We're saying, if our question was, how does a spring behave given this, would the function presented above in part A actually fit? Like, does the function above, is the function, so B is asking, sorry. B is asking, is this function consistent with, you could say, with this information? Put in English, what that means is, and the reason we're asking this is because the mass on the spring physics leads us to ask this. What we're really asking is cosine the kind of function that when you differentiate it twice, you get back itself, right? Because what Hooke's law is really saying is that the kind of function we're looking for, x, is the kind of thing that when you take its derivative twice, you get back itself, times a negative, times a constant. And the question is a cosine that kind of function? Well, we just in part A, 1 and 2, just showed that the answer is yes. Like the answer to B, the answer is yes, as long, like A cosine omega t is a solution to d2x d2 squared, as long as omega squared and k over m mean the same thing. Like, because like it's asking is that cosine function consists a solution to the second order differential equation that it's presenting there. It looks like it's just an arbitrary equation, but it's the Hooke's law equation, that thing that's presenting there. It's saying, if you differentiate x twice, do you get something that looks like that? And yeah, sorry, I don't even, we just said, this. And sorry, we don't even need to worry about the k over m thing is even another detail. We don't even, it doesn't even, we just said this. Oh, did I just lose the board again? Okay, we just said this. A page ago, we said this, but notice, multiplication is commutative. Like we just said, negative a omega squared cosine omega t is what you get when you take the second derivative. But we can just switch around the order of a and omega squared. We can just say negative omega squared a cosine omega t. And who cares? Why would we do that? Because if we do that, we notice this part right here, the a cosine omega t part, that is what we originally introduced as x. That's what we're conjecturing to be x. So evidently, if x is a cosine omega t, if you call x a cosine omega t and you differentiate it twice, what you get back is negative omega squared times itself, times the x. Like x, this kind of function does do that. Like the answer is yes. When we differentiate x twice with respect to time, we get negative omega squared times x itself. Like that. So the answer is yes, because cosine does fit that description. But before I even ask for questions or anything, let me say one of the, and that may not be the thing that people are struggling with. Maybe everybody does understand that at this point, and I can go on. But the reason there's so many exercises on the sheet is the real best way to understand what really the point of B is, or why it's asking that is to be able to see examples where something isn't a solution. Like the purpose of now going to C is just to show you that this doesn't automatically happen with everything. If we go to C, C presents us with this differential equation. It says, assume the differential equation, okay? So this is a differential equation. Again, this is what we're talking about. We're talking about something that has d2x dt squared on the left side and equals negative times a constant times the x itself. In other words, over and over again, what this course is concerned with, I want to make this as clear. I'm saying, well, all right, no, I'll say that again in a second. I'm saying this form of the equation is not a coincidence. Over and over, we're going to be presenting ourselves with d2 blah dt squared equals negative times a constant times the blah. Like whenever we see this form, whatever the constant is, as long as it is a constant, and as long as there's a negative sign before it, and the variable right after it, then it is what we're calling simple harmonic oscillation. So now in C, we're given an example of some oscillator. The equation given is this one. We're being asked to test this particular example, a cosine of 5t. We're asking, does this x function solve the above? Okay, it's the same question as before, but it's a different example now. In order to show contrast, we're going to do the same thing. We're going to test whether this function is a solution to, does solve, is consistent with, however you want to say it. We're going to find out whether this is consistent with that second order differential equation that they gave. How can we do that? Same way as before. I'm just going to differentiate 2 times and see what happens. So that's literally what I'm going to do right now. I'm taking x equals a cosine of 5. Yeah, I'm taking that. I'm going to differentiate it once. And by the way, notice what's happening here too. In part A, they told me to take derivatives and then asked me to look at them to answer B. Now C, we're really doing the same thing again, but we're kind of like, just now we're leaving it up to me to do the steps. Like the assumption is now, having done A and B, you now see that the way to test whether something is a solution to a second order differential equation is to take 2 derivatives. So now I'm just going to take it upon myself to do that right now in C, just like I did in B. And of course, I just lost my board again. Oh my God. Hold on a second. We have no internet. The answer is going to be no. Oh. And I will definitely, no, wait, hold on one second. I know it is very, today was supposed to be the day to solve problems, and this is one problem I did not. Hold on, I'm waiting for my board to come back. Of course, this makes it even harder without the board. I know, yes, I'm definitely going to upload these notes no matter what. And I hope everybody is, I want to ask and check at some point, but hopefully everybody is seeing that the notes do go into the Google Stream almost right away each time. I think. I definitely will put these notes in, and I'll do a video, even though it'll be stupid. Wait, I think I just got the board back. You know, I appreciate how everybody's running with this. And really, I really do actually like teaching physics usually. All right, I think the board is back. I even do like technology. That's good. Okay, here we are. But okay, I think the board is back. Okay. All right. I think the board is back now. Okay. So I'm doing the exact same thing as before. I'm going to take derivatives to see what happens. So I'm going to do chain rule again. Negative, like in a way, I'm skipping a step. It may bother some. What I'm really doing is going like this. I'm going negative a sine 5t all times 5, and then I'm moving the 5 out. So it's just chain rule, but physicists like to collect all the constants and put all the constants together at the front of an equation. So that might be skipping a step for people, but so I get dx dt equals negative 5a sine 5t. Then I take the derivative again. Okay, d2x dt equals, I take the derivative again. So there's chain rule again. In other words, the 5 comes out again. So now I get negative 25. Still the a just sits there, but now cosine turns back to, sine turns back to cosine. And so I get this. And notice what it's trying to show is that this is the thing with cosine. Cosine is a function that when you differentiate it once, you get something else that's related but different called sine. But then you differentiate that and you get back to cosine, but with a negative sign and maybe even some other junk. Cosine, when you differentiate it twice, you get back itself times a negative. That is precisely the function that is demanded by Hooke's law. And it sort of does make sense because Hooke's law is about a spring going back and forth and back and forth. And cosine describes something going back and forth, back and forth, back and forth on a graph. Cosine is the graph of what we're talking about physically here. But anyway, I get this d2x dt. And then I look at it just like before. I look at it, or maybe I first say, oh yeah, multiplication is commutative. Oops, sorry. Multiplication is, oh yeah, so I already did the multiplication. So multiplication is commutative. So I have that. So I say, oh yeah, wait a second. This piece right here is what right from the start I called x. So apparently, if I differentiate this function twice, I do get back a cosine. And here's where you have to be careful. Like, I do get back a cosine. I even get back cosine of 5t. But apparently what I get back is negative 25 times that original x. Because, one second. Oh, okay. I will start, but I've had problems all day. I've got to teach. I will soon, but the class has had difficulties. I will be there. Felix, please. What was I just saying? Oh. Right. So, okay, back to this. Here's now why, even though good things are happening and what I'm doing here is right, like I just mimicked what I did in part A and I'm doing it again. But now it may look wrong or it's ending up looking different. And that's for a reason. Like what I end up getting here is if I differentiate twice, x equals a cosine 5t. And that was like one of the two givens that I'm sort of like trying to relate here in question C. If I differentiate that twice, what I get is d2x dt squared equals negative 25x. I get this line here at the bottom. That is not what was presented in part C. Like, in other words, x equals a cosine 5 of t apparently is a solution to what I wrote at the bottom here. It's a solution to that. But what I wrote at the bottom here is not, like 25 does not equal 3, to put it as simply as I can. 25 does not equal 3. So this cosine solution here is not a solution to that particular differential equation. These questions are just trying to get us used to the language in a way. But I'm saying that if you ever have something that looks like Hooke's law, the solution will be some kind of cosine. But very specifically, well, basically what I'm saying here is this. I just lost the board again. Oh, God, sorry. This is really frustrating. I was just about to write, sorry, I just lost the board again. But what I was just about to write is what we're trying to notice here that it's so important is if you ever get something that looks like Hooke's law in math terms, and I really do want to write this down, but if you ever, in physics for the rest of this course or in life, if we see an equation that says d2x over dt squared equals negative constant times x, then necessarily the solution will be a cosine, but with an angular frequency with an omega that is the square root of that constant. That's what we're really trying to say, that I really want to write down on the board. But what we're trying to say is all harmonic oscillators are described by that differential equation, because that differential equation is really Hooke's law. And all of them are solved by a cosine. But it's always cosine of omega times t. Omega is angular frequency. And what I'm really trying to say, that if, whether I can put it in this board or not, if nothing else, the big takeaway so far of this is for a cosine, for a particular cosine to solve a particular Hooke's law situation, the omega of the cosine has to be the square root of the constant in the Hooke's law thing. I'm going to try, I know that's a mouthful. I'm going to try to write, bear with, I'm going to try to get the board back and write that down, but that is the key. Like, that's why B works and C doesn't, is that the omega has to be the square root of the constant in Hooke's law. That's what we're trying to say. It would be better if I could, bear with me one more second if I could, but that's the same theme that's going to run throughout D and E and F. Like, in fact, yeah, all the way through F. That's what it's going to be going on. Oh, my board is coming back, we hope. Okay. Okay, here, I can't get, here's the most concrete thing we could do right now. And I know we only 15 minutes, and I know this is just get like one step forward and 85 steps back each time. But if we're focused on C right here, again, C looks like the same type of question, but this time you get an answer no. Here's what I think everybody could do right now to make this as concrete as possible. If you look at C and just look at that differential equation that it's referring to, d2x dt squared equals negative 3x, okay? You can pretend, what we're trying to say is that 3 right there, like that form of that equation means really that's Hooke's law. It's just written in calculus language, but that is Hooke's law. And specifically, specifically that 3, and please try to write this if you can, even without my board. Again, if I get the board back, oh wait, maybe I've got it. But that 3 right there, not the negative, but just the 3, think of that as K over M. Think of that 3 as K over M. If that 3 were K over M, what would be the angular frequency of that oscillator? Like, how many radians per second would it be doing is what I want to ask. And I guess I'll just say, because this is getting so abstract, what I'm trying to say is it would be doing square root of 3 radians per second. That's what the 3, it wouldn't be doing 5. It would be doing square root of 3 radians per second. Whereas the first part of the sentence seems to imply 5. All right, I think I got the board. This is probably the last time I'm going to try, and then we're just going to, but I'm just, well, here, okay. Well, in general, what we are trying to notice, believe, or understand is this. What really, 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 and here I'm going to write on the next board, but this is the biggest takeaway. Oh, just lost it again. I can't, I'm sorry. The last 2 letters of that board were about to be omega times t, just as you might expect. Oh my God, this is ridiculous. Uh, uh, the, what I just wrote really is actually the everything of everything. And all this takes a while to get used to. And by the way, this stuff is hard. Like it is just hard, even under the best conditions. And it is unusual stuff. It is new. It's a new level of physics and math for all of us, honestly. And it was for me the first 85 times. There's something about it that even if we all were doing perfect, it takes many times looking at this because it's a different way of thinking. But the one thing I'm just trying, but if there's a big takeaway to apply to problems, it's that notice in the board I was just trying to write, the very last board I'm trying to write, notice all of a sudden there's the letter Z there. Like focus on that for a second. I mean, even if you're desperately trying to follow me, just like I'm desperately trying to have us all follow me, even if you've been following me, all of a sudden on this last board, I just switched from all the X's to a Z. That could be a very confusing thing that I just did that, but that is very on purpose, very on purpose. The reason I just switched to a Z on that board, and I think you could complete the board. The last two letters are just omega t. But even if it doesn't look like it says anything new except it has a Z in it. But what it's trying to say on that board is, look. Physics brought us to a particular relationship. But then that relationship we're analyzing mathematically. That means, like, to analyze it mathematically means to not care what the exact numerical details are, like whether is to analyze it with variables and constants, letters, rather than numbers, right? And to believe that the math, if the math works at all, then it just works, and it doesn't matter whether it's a heavy spring or a light spring or a pendulum or something else, some other kind of oscillator. That's all true. It's so true that actually even the letter X stands for position on some kind of one-dimensional line. We originally came to this math because we got brought there by Hooke's law, which specifically looks at X positions on a line. However, what I'm here to say, if I can get nothing else across today, is actually everything mathematical that we've been saying about X doesn't care that it's an X. It could have been a Y, right? Like, duh, I mean, who cares what letters? It could have been a Y or it could have been a Q. It actually could have not just been a different letter, but it could have been measuring a totally different thing. Like, in fact, from here on in, I'm changing the X to a Z because of what I'm trying to say. The math that we're kind of trying to practice and see here is whenever some variable, some dependent variable, whenever some dependent variable seems to obey that equation, like whenever we have evidence from the lab or from somewhere to suggest that some dependent variable like X or Z or Q or theta, any dependent variable, if its second time derivative equals a negative times a constant times itself, if the rate of change with respect to time of some variable is directly proportional to that variable itself. And that's what we're saying here. Like, so again, I don't care if it's X, I don't care if it's Y, I don't even care if it's theta. So therefore I'm calling it Z just to mean any variable for all time. If the second time derivative of that variable equals a negative times some constant times that variable, then that variable is oscillating in time at a rate which is at an angular frequency rate, which is the square root of that constant. Like, that's the part I'm really trying to write down on the board that can't now. But like, this actually is like all of those many examples on the mathematical sheet. I mean, on that section of the mathematical methods sheet, like over and over with all these derivatives and E and cosine, all that. And I still will finish it. And I still won't assign anybody anything new until I go over those. I promise. Like, I'm not going to leave it hanging, but I'm obviously not going to get to it right now. But what I'm trying to say is that all those seemingly different looking examples are actually trying to just sew together to say, look, from now on, we don't care what the variable is. If there's some measurement in the world that says that if there's some measurement in the world whose rate of change in time somehow is directly proportional to that variable itself, like we have here, like the acceleration of a mass on a spring is directly proportional to the position of the mass on the spring. So in other words, the rate of change of position is a negative times a constant times that very position. Whenever we get that about any variable at all, then we know from this math that we're doing here that that variable must be oscillating back and forth, like, and you'll see in the next homework, even if that variable measures temperature, like the next homework looks like it has nothing to do with anything. The next homework gives an equation that seems to be talking about a temperature system, and you very well might look at that homework and go, where did temperature come into this class? What the heck? We don't know how to do temperature problems. But we're really just trying to say, no. It's the same math. We're asking about the math. We're saying, imagine that we measure some temperature, for example, and if the temperature follows D2 temperature over dt squared equals negative times a constant times that temperature. If the temperature could be described that way, then that means the temperature is going up and down, oscillating at a angular frequency, at a steady constant angular frequency, and the frequency, the angular frequency, omega, will necessarily be just the square root of whatever that constant was. Like, that's how simple and elegant this is. We're saying from all time, anything that can be described by that differential equation will be an oscillator, and it will be an oscillator whose angular frequency is known right away, is simple, is constant, and this, to bring it full circle kind of to the Robert point, or part of the Robert point, like that's such a magical thing to have discovered. And it really is. It's super powerful, and it underlies PChem and we're never going to leave this harmonic oscillation thing. That is why we're spending so much time on it. But it's a recognition that in nature, from now on, if we ever see a system that's described by that specific second order differential equation that we're studying, then we'll know right away, oh my God, even if we didn't expect it. If we're looking at color, if we're looking at temperature, if we're looking at electric field strength, if we're looking at atomic bond strength, if we know for some reason, if we have a graph or something that suggests a differential equation of that kind, then we know that that variable, that measurement, is oscillating at a known constant angular frequency, which does not depend on anything but the ingredients of that oscillator, like an angular frequency that does not depend on amplitude. That's what we mean by harmonic. I mean, and Robert's absolutely right that we didn't say that at the beginning, and it is a choice. Again, maybe it's a bad choice, but we kind of like, because it wasn't said at the beginning to the physicists that discovered it either. Like, our point is that by analyzing the system, we've now discovered properties of it, the key property being that the angular frequency is so knowable, so derivable, so instantly like knowable once you know the ingredients of the system, and won't even be affected by amplitude. That's the math takeaway, and it will be true of any variable at all that differential equation is expressed. So we're just really trying to get used to that equation. I mean, and I know in most classes, like, you get used to one or two equations as an example of like a whole larger mess of things that then you're then expected to. We're not actually saying that here. We're actually saying we're really trying to know this equation. But in order to know it, this d2x dt thing, we were trying to back up and do simpler versions of it, like dx over dt. Like, that's what last class was. I was trying to just make simpler versions of this equation so you could really see what its nature was, but it is about this. But I know this is all crazy. I didn't get the board back. I'm just babbling. And I don't even my glass. I appreciate how hard all of you are trying, and that you're sticking with this at all. And again, I used to say to everybody back in the building at John Jay, I mean, when we were there and stuff. And again, and really, I don't love these conditions at all. And I love them even less for you and for my own children. I think this all sucks. But obviously I'm not doing so well with it. But even in the best of times at John Jay in the building, for whatever it's worth, I used to be a little bit better at pep talks and stuff. And I used to tell people something I still very much believe, which is that this program, this forensic science program, and some of you might be in this class for other reasons, but in particular, this forensic science program at John Jay that I'm very, very proud to be part of, believe me, as much as I complain, very proud to have a job in it, because I think blah, blah, blah. I could not have survived this program as a student. I just want to make that clear. I think I'm a smart guy, and I think I know me some physics at this point, and I've definitely worked hard at my things, and my major was hard, but this major is really hard. It's really hard. And I'm not saying that as an excuse either, but I mean, the whole thing, getting through it in the best of conditions, is hard. And the thing is, yes, it is really hard. It's harder than you guys know. I mean, because it's hard for some smart, really enlightened reasons, and it's also hard for some dumb reasons. And it's hard in ways that Harvard is hard, and it's also hard in the way that like Votech school is hard. And I'm not kidding about either of those. And very few people go to both of those kind of schools. And when yes, that's right. That's right. I'm looking at the chat. And yeah. So as long as I still have your attention right now, and I'm not saying any of this to defend me or anything, but I'm saying even in the best of times, this major is freaking hard. So, so why do people do it or whatever? Well, of course, I think it's valuable and that you learn stuff, but putting that aside, people get jobs from this major and people get into graduate school from this major, and they get it in jobs in graduate schools a lot more than a lot of people in other programs that John Jay or CUNY do. Like this program puts people places for a very simple reason. Even on its worst day, people will get places for having finished this program. And the very simple reason is exactly what Isadora just wrote in the chat, and actually, I don't know if that statistic is exactly right that Isadora wrote, but what is exactly right is a lot of people don't make it to the end of this major, and everybody knows that. And I'm not saying that to scare you at all, any of you. First of all, if you already got this far, you've already gotten past hump number 1 of the major. I don't want to scare anybody, but I want to say the fact that people don't make it to the end, whether they either get counseled out or they drop out or whatever, is precisely why the degree matters. Like means something. It's why when you get this degree, you will get a job, like maybe not right away, but why you'll totally have my respect, whatever that means, and you'll my recommendation and all that, but you'll also really have the respect of the outside world, deservedly, because everybody knows it's not a joke, because it is possible to fail this program. Therefore, if you don't fail it, you've done something. That is really meaningful. And it's not true of a lot of programs and a lot of GG colleges, and everybody know, like private swishy colleges. There are colleges and there are programs where people get through no matter what. They just get through because that's what they're paying for, the right to get through. That is not what happens here. No one like just gets you through, right? And again, I'm saying that as praise, because what that means is if you guys do get through this shit, then you've done something for real. And now to bring to and what's the trick for getting through? It's not always just the geniuses who get through or something like that, or just the people whose like parents did something. The people that get through this program are the people that don't stop doing the program. It actually is that simple, because everybody has a crisis at some point. Hopefully it's not now, and I know we have to go, but I'm using this as a microcosm. The point is everybody gets a crisis at some point in the program, goes, oh my God, is it either can I really do this, or is this really freaking worth it? And the answer is yes, if you say yes. Every time you're about to have a crisis, if you just actually don't drop out and you just keep doing the next thing, whatever it is, and you just try to get through the next thing and don't worry about the last day of graduation or whatever, but just get through the next thing and and don't assume you have to be a genius to do it, but just that you have to get it, then, right, okay, cool, thank you, Ray. It's really true. Like any of the hard things that I've gotten through, I did not feel qualified when I was doing them either. I faked it till I made it, just like all of us do. And, and some things I don't fake anymore because I did make it, some things. But how I got there was I just keep doing it until someone forces me not to. And that won't happen to any of you if you keep doing it. So just like with this class, like, believe me, I know who's fucking this up. It's not you guys. Okay. So if you just keep staying with me, even if you don't feel like you know what's going on and whatever, I know what the problem is. So anybody who stays with me, whoever's standing at the end is getting good grades, obviously, because there's going to be enough bad grades for the people who just drop out and go AWOL and just take the F and don't even come back to argue it, right? Like, just don't be that person in this class, and don't be that person in the program. And then you get through the program, and then on the other side, you'll understand the things that you were supposedly learning here that nobody ever learns the first time, ever. I didn't understand any physics until I taught it like a bajillion times. I'm just saying that. I'm partly saying it to defend myself, to ask you to stay with me and apologize, but I really do mean it. It's a speech I used to give more convincingly when we were all together and actually doing stuff at John Jay. But I'm going to run now because my son's going to kill me. You're going to kill me. I will post everything. Just do, but in my class, wherever you're stuck, just admit it to yourself and just do the next thing. If you're still on homework 1, go back to homework 1. And anything you hand in, I will give you credit for. It's not about time. It's not about the clock. It's about understanding the next thing, all of us. Okay, that's how we're going to approach it. And I'm going to go right now.